So we will continue with topic 2.3, pressure and head. So in a static fluid of a constant density, we have a relationship dP over dz over rho g. In previous video, you have been introduced to delta P equals to negative rho g z2 minus z1, which is delta z. Okay. So this is in the differential form. dP over dz is equal to negative rho g. And this can be integrated to give us, so if you integrate this both sides, okay, you will get P pressure equal to rho g z plus a constant. Okay, for a fluid with a free surface, okay, the pressure at any depth z, okay, is measured from the free surface, from the top. So here, it will become z is equal to negative h because we measure it from the top. So if we replace negative z with h, you will get p equal to negative rho g z, right, initially. So z we replace it with negative h plus constant. So the negative sign will cancel out. So P is equal to rho GH plus constant. So what is this constant actually? So at the surface of the fluid, we are normally concerned with the pressure is actually the atmospheric pressure. So the term constant here is actually your atmospheric pressure. So P equal to rho GH plus P atmospheric. As we live constantly under pressure of atmosphere, everything also exists under this pressure. It is convenient to take the atmospheric pressure as datum. Datum is another name for a reference. So atmospheric pressure is 1 atm, okay? 14.7 psi. So what else? 101.325 kPa, and you can find other units, okay, that equivalent to atmospheric pressure. So since we take the atmospheric pressure as datum, we quote the pressure as above or below atmospheric. So pressure quoted in this way is known as gauge pressure. So your term here, rho GH, is also can be simplified as pre-gauge. So your P is equal to P gauge plus P atmospheric. Okay, that P, okay, the lower limit of any pressure is 0. That is the pressure in a perfect vacuum. So pressure measured above this datum, okay, is known as absolute pressure. So the previous term just now, this P is actually P absolute because we measure it above P atm. If it's below, then it will become P vacuum. Okay, so this is the equation for absolute pressure. Okay. As G is approximately constant at any height, the gauge pressure can be given by stating the vertical height of any fluid of density P, which is equal to pressure. So this is the term for gauge pressure, and we call this H as head of the fluid. Okay, head. If it asks you what is the head of the fluid, that means it asks for H. Okay, head. Don't get confused with height. Okay, previous term we call it height, but now it's head of the fluid. So if the pressure is quoted in head, the density of the fluid must also be given. So next, we will try to solve one question related to this shortly. So this is the diagram to show the red line here is your datum, your reference line, okay, which is the atmospheric pressure. So anything above the atmospheric pressure is your gauge pressure, and anything that is below that is your vacuum pressure. So if you measure the whole thing, you will get your absolute pressure. Okay, absolute pressure is equal to gauge pressure plus vacuum pressure, which because this is already include the atmospheric pressure. Okay, so let's try this example. A cylinder contains a fluid at a gauge pressure of 350 kilo Newton per meter squared. Express this pressure in terms of a head. Head here is the H, okay, of water. They give you the density of water, and then mercury. They give you the Sg, okay, relative density of 13.6. And part C, what would be the absolute pressure in the cylinder if the atmospheric pressure is 101.3 kilo Newton per meter squared? Okay, so let's try. So part A, so you need to calculate the head. So H is equal to pressure divided by rho G. So the pressure is given as 350 kilo nano Newton meter squared. So since we want to write it like this first, 10 of power 3 for kilo Newton per meter square, and the unit for Newton, okay, you can actually replace it with, okay, I wrote this here. Newton is equal to kg meter per second squared. So I will just replace this in here. Okay, kg meter per second squared over meter square. Okay, divide by your density 1000 kg per meter cube, and gravitational force is 9.81 meter per second squared. Okay, so this term second square cancel out. So your m here cancel out with this, so you have 2, and this one m, you have another one m. Okay, this one m cancel out, so you left with just m, and kg will cancel out. So your h, okay, plug in this in your calculator, you will get h as 35.7 meter. So this is the answer for part A. So for part B, I don't have space there, so put it here. Mercury. So you want to express the pressure in terms of a head of a mercury, and they give you a relative density of 13.6. So remember, Sg is equal to rho over rho H2O. Okay. So if you want to know the density of mercury, it is equal to Sg multiplied by rho H2O. 13.6 multiplied by 1000 kg per meter cube. So your density of mercury is 136.00 kg per meter cube. Okay, next, you use the same formula to calculate for head. M is mercury, yeah? So 350 times 10 power of 3, okay, kgm per second square per meter square divided by 13600 kg per meter cube multiplied by your gravitational force. Okay, use the same. Okay, this one become 2 and M. So kg cancel out. So your H is, okay, plug in this in your calculator and solve for H. You will get H as 2.6 meter. Alright, then the last part. What would be the absolute pressure in the cylinder if the atmospheric pressure is 101.3 kilonewton per meter square? So recall back the formula for absolute pressure. Pabs is equal to P gauge plus P atmospheric. So P gauge they give you as 350. Okay. KNM plus PATM 101.3 K. So add these two, we will get 451.3 kilonewton per meter square. So this is the answer for part C. So that's all for topic 2.3. For the next topic, we will continue in next class next week. And please make sure you fill up the attendance form and answer the question there. Alright, thank you.